Okay, so this is the second lecture on neurosymbolic AI. And I'm just reviewing a little bit of these slides for 5 minutes, and then we'll move on to the second lecture. So this is a synopsis. We began last time by talking about these three books: Deep Learning, which is Goodfellow, Bengio, and Corwell. We are assuming that we've digested all there is to know about deep learning, discriminative models, generative models, so on. And then there is Probabilistic Graphical Models, which is the second book here, which is all about reasoning with probabilistic structures, Bayesian networks, where there are dependencies, causal models, and so on. And that is all about symbolic reasoning. And then the third book is Thinking Fast, Thinking Slow by Daniel Kahnemann. And that book is about how humans perform with two different systems in our heads. These two may not be physically separate, maybe the same part, we don't know. And so, but it provides an interesting architecture where we can have both deep learning and probabilistic graphical models in the same system. So that's what our thinking is. And let me skip on to the slide here, which talks about the summary of the two systems, is that we have a conscious brain, which is a slow brain, and a fast brain, which is actually things like recognizing things and so on. So they show it by a hare and the tortoise. The fast brain is fast, and the slow brain is the tortoise, which is slow and it is more deliberative. So system one is fast, system two is slow, and system one is unconscious, and system two is conscious. And system one is automatic, and system two is effortful. Everyday decisions done by system one, and complex decisions are done by system two. System one is very fast, but it can also be error prone. System two is more reliable, right? So that's the kind of thinking that we can all relate to. And let's see. When the problem is too complex for system one, system two kicks in and solves the problem. And so that's another key slide there. And so let me see which ones we want to go to. Okay, there is what's called as information consciousness, I consciousness. That is the system two part. Ability to solve possibly complex problems by recognizing necessary processing steps in specific context, tackle the desired problem. This is the information consciousness. We're talking about how the human brain, this is the kind of words that psychologists use. Information consciousness related to system two's high fidelity processing mode, considering a problem and harnessing the relevant faculties of our cognition to devise a plan to solve it. Now, let's say I ask you to do 17, what is 17 times 24? All right. I mean, it's not something that's going to occur to you off the top of your head, like, how much is 2 plus 2, right? So you'll have to deliberatively think about how would you multiply two numbers, and you have to bring your information consciousness to do multiplication of two numbers and so on. And there's a plan to solve the problem, what is 17 times 24. The other consciousness, they named it as mystery consciousness, M consciousness. This is the ability to build a simplified, approximate, and subjective model of people's and other minds, beliefs, and intentions. A low fidelity model building can be linked to system one, as system one is able to form a rapid but usually inexact model of the world. So it's a bit like the networks, which makes some kind of a model of the world, and that's very, very fast in performance, right? So humans excel at I consciousness, while many animals and primates possess various, animals and primates, or dogs and cats, they all have M consciousness, mystery consciousness. They all have neural networks, but it is humans who are good at I consciousness, and that is we are able to think of the problem, 17 times 24 and so on, right? So that's the kind of thing. Okay, so that was a very quick recapitulation of this one, okay, of fast and slow thinking. So we can now go on to talk about the 10 research problems of system 1 and system 2, and what are the kinds of things one could do. There's a certain theory about having both systems, and how would they, how could we think of these kinds of architectures? And so we're going to start listing out all of these problems. And I just need to figure out how to share this again. All right. Research topics. Okay. All right, there we are. Research topics in neurosymbolic AI. More specifically, these research topics are research topics in system 1 and system 2, and on slow and fast thinking. How could we apply these? I mean, we are coming from the point of view that deep learning on its own is not the ultimate thing, right? We saw some examples of natural language and so on last time, where a pure deep learning solution, even one of the impressive BERT or GPT-2 for NLP, might fall short, giving you answers that are not quite right. So where do we go from here, right? So that's where we are. So, and how could we possibly use Kahnemann's idea? And so here are the 10 topics. All right, there is a paper that describes these 10 topics. It just appeared a couple of months ago. The topics are capabilities of systems 1 and 2. All right, what can systems 1 and 2 do? And then we ask, is system 2 inherently sequential? System 2 is a logical reasoning one after the other. So is it always going to be a sequential system that is one stage to the next stage to the next stage? Or can it have somehow be parallelized? And the third one is metrics to evaluate the performance of systems 1 and 2. How do we evaluate the performance? And how can there be introspection in systems 1 and 2? That is, trying to explain what is system 1, how did you get the answer? And then switching between system 1 and system 2. You have two systems and we have solved it using one, we can also solve it using two. And once you become adept at solving the problem using two, can we somehow switch this into the other? And how to reason when using both systems 1 and 2. If you've got both systems operating at the same time, a symbolic reasoning system and a deep learning system, how can we use both? Ethics theories, wow, tied to systems 1 and 2. I guess it's got to do with explanation and bias and things like that, right? And then we talk a little bit about definition of abstraction, because we're talking about the key point. My next lecture after this research topics is over, we'll talk about what I call a robust AI. And there we talk about abstraction as an important concept, that it's not just at the low level instance level that you're interested in reasoning. You also want some abstraction of the concept. And how do we get that? Using maybe attention models or knowledge graphs. By the way, knowledge graphs is a topic I plan to go over. I think it's a worthwhile, important topic. I don't know if knowledge graphs are covered in any other course, right? Is there any course where you study knowledge graphs? Anyone know? Okay, all right, we'll go over it. I have one lecture on knowledge graphs. We'll cover. Knowledge graphs are the kinds of things that we encounter whenever we do a Google search on some topic, right? You want to make a Google search on, say, Joe Biden. It'll make on the right side, it'll give you some kind of a table which shows Joe Biden is the president of the United States. The previous presidents of the United States were all these people. And you say Joe Biden is married to Jill Biden. And Joe Maris, it gives you all kinds of information other than who's Joe Biden, and it gives you all kinds of history and so on, and nicely structured. They put it on the right side. I believe that's what they do even now. Is on some topic, searching on some topic, or even like a city, right? You search on Buffalo, New York, and you end up getting all kinds of information about New York State and all these things on the right side. And that's all in the form of a knowledge graph. And that is being presented to you as useful information. So how do they structure the graph of information? Anyway, and then combining multi-agent systems is topic number 9. And last one is architectural choices for supporting this vision of AI. So what are the architectural choices? Okay, let's see I think I have a slide for each of these. So capabilities of systems 1 and 2, clearly identifying capabilities of systems 1 and 2. What are they designed for? Is it designed to recognize what kind of an animal it is, right? Something, in one of those data sets. What features would they use? Like one of them learns these features, the other one maybe other features. So systems 1 and 2. How are these two, the fast and slow thinking architectures, designed? Is system 2 inherently sequential? The human system 2 is sequential. So if you have to reason through, if I say, a student got a job offer at, I don't know, maybe Google research gave a particular student a job offer, then we kind of reason through it sequentially, saying, okay, to get a job offer at Google, the student must have done well, must have got a good recommendation letter, and must have had good scores in the SAT or whatever. And so in order to get a good score in SAT, the student must be smart. The student got a good recommendation letter. The student must have got a good grade in the course, and so on. We can kind of logically reason through as to what are the implications of something you're observing. And that's all sequential, right? We're going backwards, saying, okay, the job offer means good recommendation letter. Good recommendation letter means good performance in the course. Good performance in the course means student is smart, or the course is easy, right? It's like 4 steps there, going from job offer backward. The reason I'm giving you that example is that's the example in the Probabilistic Graphical Models book, which we go again and again over it. And so that is sequential. So is that always sequential? Should we exploit parallel threads performing system 2 reasoning? That comes about naturally. It's not a very complex topic. Would this, together with greater computing power of machines compared to humans, compensate for the lack of other capabilities in AI? So if we have such a sequential model that will actually reason through at a symbolic level, it would not be at the level of lots of examples of these where you learn the intermediate steps and so on, but at a symbolic level, how would you combine these things? System, so okay, this one is only system 2 inherently sequential. Okay. Metrics to evaluate the performance of systems 1 and 2. Of course, system 1, accuracy, precision, recall, F measure. So the standard measures for system 1, the neural network is measured typically like that, right? Now there might be a few others, but those kinds of measures. And system 2 is correctness of conclusion. If you have concluded symbolically from the fact that the student received a job offer, then we have concluded that student is smart. Is that a correct answer, right? Correctness of the solution. Maybe it's a probability associated with it. In a combined system, switching between the two, so metrics for combining systems. All right, introspection in systems 1 and 2. Can M consciousness alone solve complex problems that in humans needs also sophisticated levels of I consciousness. So M consciousness is neural network. So can neural networks alone solve complex problems that in humans need also sophisticated levels of I consciousness? It is not just it flashes to you what it is, but it takes you into a more complex reasoning. And how is introspection linked to autonomy and human-machine teaming? All right, this is a more complex thing. So we're talking about systems where you have a human and a machine interacting. And let's say, is introspection a binary concept or should it have several levels? If in levels, how can we associate different capabilities to various levels? So is introspection a binary concept? Yes or no, right? Student is smart or not? Student got a good recommendation or not? Or it could be, probabilistic, I suppose. Should we have, and that's what PGMs directly give you. Probabilistic graphical models are always trying to compute probabilities. So what's the probability of the student being intelligent, and given this, and so on. Should we have models of the agent's minds, those supporting M consciousness at different levels of precision fidelity? So that would be another level of
Professor.
complexity. Yeah.
Yeah, I had a doubt. So I just wanted to know where we are drawing the line between the M consciousness problem and I consciousness problems.
Hmm.
For
You know,
example,
yeah, good question. What,
yeah,
where are we drawing the line between the two, right?
yeah, exactly.
Hmm.
Because, for
Right.
example, now in both, like if we say that systems are like we are making the humans as the point of reference, like what humans can think in the
Can
first
you
of
can you make your video come alive? Who am I talking to?
oh, my video system is not working, sir. That's
Oh,
it.
you are the videoless person. Okay, all right. So let me just answer the first level question. Maybe you had more to it. That is, where do we draw the line between system one and system two? Where we are coming from is, on the one hand, we are saying deep learning doesn't do everything you would like it to do. It seems it can't even solve a FISBUS problem. Exactly. It'll give you 99.9 accuracy in solving the FISBUS problem. They try to solve the FISBUS problem, training it on numbers 100 through 1000, and they tested it on numbers between 1 through 100, right? They wanted to give a different data set to test it on. It did pretty well, in terms of fizz or fizzbuzz or giving the number, but it is like 99.9%, 99.8%, something like that. And what does it mean? Even a simple problem like this, you can't solve exactly using deep learning. And whereas a logical system which has been programmed and learned the rules of division 3 and 5, and it does very well. So we know that there are two solutions to the problem. And of course, the second solution, I didn't say how it's learned. The first solution can always be learned using back propagation and all that. So then we're saying there is this issue in AI. And then the psychology guys, Kahnemann and so on, economics guys and so on, they are saying anyhow your brain has got the same way. There are two different ways of working, and we transfer things from one to the other and so on. And so now the AI guys are saying, look, we've been struggling with this issue. We solve the problem with the one or the other, and we need to somehow bring them together. And you're saying that's how the human brain is also like that. Then let's see what kind of architecture can we do. So we really don't have any answers to this. We are just saying that these exist, and how would we go about architecting this? It's a speculation here, but there is a good reason for it, because intuitively we think you're right. System one and system two exist in our brain, and maybe that is how we do well. Otherwise, silly that a program which is very sophisticated deep learning system can't understand that the solution is based on dividing by 3 and dividing by 5. It is giving you a rote answer, although there's generalization. It has never seen the numbers 1 through 100. It's only seen 100 through 1,000, and it's able to generalize to 1 through 100, but it still doesn't get the concept, exactly. That's such a simple concept. So what is the solution? How do we bring this together? So that's all we are saying. And these are all some ancillary things some of these guys have tried to write down, saying what kind of problems could there be. You may want to read the paper I indicated. That gives you a little bit of more of an insight on this, but not much more. They're saying this is kind of futuristic thinking. Please select one of these problems and see what you can arrive at. You're not saying, so these are all problem definitions rather than solutions here. So we're starting with something intuitive and going into something very concrete. So that's the challenge here, which is why we need all of us to think about how would you do this? Even thinking of very simple, that's what I wanted you to think of, a very simple problem. And then think about, how can I take advantage of these both? What are the pluses and minuses of these, and what could be a solution? That way, you would have brought together ideas of deep learning, Kahnemann's thinking fast, thinking slow, and if you use the probabilistic graphical models approach for the second approach, the second symbolic approach is, I need to learn the logical sequence, the causality in this problem, and that I will describe the PGM solution to learning causality. It's a challenging problem from the point of view of computational complexity, but we will talk about it. All right. I don't know if I answered your question. So now ask me again.
Yeah, sir. Actually, I had like what I was thinking is like we have a deep learning model which is working. So when can we say that, okay, it doesn't require the I consciousness, it's working on M consciousness and it is giving the good performances? Like what are the metrics which will be, we will be using to decide if the machine needs the M conscious, like the I consciousness, or it is like, capable of, like it is giving good performance on M consciousness itself.
Well, we're saying that 95% of the time, the M consciousness is good, even in human beings. Same thing in a neural network. It does very well on a lot of the cases, but it does fail, and particularly some unusual things. You can't trust it fully, is what we are saying. And in language, it shows up a lot. It just cannot figure out the logic. It figures out all the English part of it, because it has, GPT-2 or GPT-3 have been trained on an enormous amount of text. And it gives you very sensible. Alexa is able to answer your questions extremely well because it's been trained on a lot and lot of data. But in some critical, or even not so critical scenarios where it has to do some reasoning based on what was said earlier on, and it hasn't learned the neural network structure. The attention models are just going about by what is the relationship between words. It's all on words it is learning. It is not at the conceptual level. It is not doing some reasoning around it to give you an answer. So they are running into a roadblock in this with Alexa. And like that, even this FizzBuzz problem, we are saying we're getting 99.9, but then what if I give you some number which is a 17-digit number which is divisible by 3 or 5 and so on? Can you trust it? Because you will say, oh look, it does 99.8 even on the testing set, which is never seen, but the testing set can be anywhere. So the theme here is the deep learning methods do well. We generalize it, we regularize it, it goes outside the training set, but still it has missed the central concept. Like in the case of FizzBuzz, all it had to do was learn divisibility by 3, divisibility by 5, and there is no checking that it has learned that concept. If only it had learned that concept, you would say, okay, it's a trustworthy now. It knows exactly what to do. Even just a child knows how to divide by 3 and 5. You can trust the child, as opposed to giving so many examples and saying, okay, that's how it was. It's figuring out all kinds of connections between these numbers, which may be irrelevant to the main concept. So so we know that there is a deficiency, and we are trying to see what is it we can do to remove that deficiency. If you can take, actually, we will talk about a FizzBuzz as a solution, a logical solution, how you can learn FizzBuzz. There's logical solutions, by the way. They usually work well without noise. Supposing you give a sequence of logic rules for FizzBuzz, it will learn it with a few statements, propositional statement. It learns it. But what if I throw some noise into it? Then it gets thrown off. And so what do you do in that situation, and so on? Whereas a noise is something that neural network is good at. So neural networks are good at dealing with noise. If some of the numbers are off by a little bit, it'll still get a fairly good solution, even if the input output was wrong. Like, I give you lots of good examples to train on, and I give you a few bad examples to train on. Neural network will not be thrown off. Whereas a pure logical reasoning system, that will get really confused if I give you some wrong examples as input. And how do we make it tolerant to noise? So there are these kinds of issues that come in when you try to put it together. All right. Okay, so anyway, bear with me as we're going to tread through these areas where we are speculating, which is why I'm asking you also to think about what kind of a problem, and we'll elaborate all this a little bit more as we go along. And so these are all, just take a look at this original paper. By the way, the link that I gave, where I got this from, is this particular paper. It's 15 December 2020. So this is not more than 2 months old. And they came up with a nice set of problems, which is what attracted me to that paper, saying, well, here are some problems you can think about. And so, if you find that it's not being explained well enough, you can go to some of the sources they may give and say, all right, let me go there and see what they're saying. All right. So where were we? Introspection systems 1 and 2, and governance, just switching between systems. AI system should be able to recognize when it needs to deploy capabilities from system 1 or system 2, and also when to switch between the two systems. In humans, such a switch depends on many factors, including framing, priming, and the context of the decision environment. In an AI system, there seems to be other factors that make up the sufficient conditions for this switch. Example, when system 1 cannot find a solution. So the switching between the two. So is there, we just give some intuitive idea, right? When you keep on doing the same type of problem again and again, each time you have to do some thinking, just like, finding your way to a classroom. After you've been there a couple of times, you don't need to think, you just go there. So that becomes say system, started out as system 2 function, how you find your solution. And when it becomes a system 1, it is just giving you the exact route to get there, right? I guess some of these mapping systems we have in cars, I guess they would just, between 2 points, when they tell you what the directions are, I guess it's all been learned earlier on and they present it to you very quickly. But the first time around, they need to figure out what is a good solution, what's the best route. We may need to switch when we are facing a very high stake decision. A mistake may confer dangerous consequences according to some high weight criterion, or also when the decision needs to be explainable to a third party. Yeah, that is a known inherent drawback of deep learning is, if it's able to recognize something, right? One of those 1,000 classes or whatever, right? And if you ask the question, how did you say it was a particular breed of dog, then it has to be explainable and not simply say that these were the values of the hidden layers. So some kind of intuitive solution might have to be presented, which calls on system 2 to be used for explainability, whereas system 1 is being used for performance. Actually, I have a lecture on explainable AI. Maybe I should also go over that part. There are so many people have thought of this issue of explainable AI, explainable deep learning, and suggested this is how we could do that. Only thing is when you build a system 2 as opposed to system 1 for the same problem for explainability, the system 1 may be very efficient and system 2 is slow, and system 2 is actually doesn't exactly correspond to how system 1 worked. So there are mismatches that are possible. So how do we do that? If we, do we use two systems or do we use one? How do we switch between the two? Reasoning when using both systems 1 and 2. When there are two or more diverging policies or heuristics offered up by system 1, one needs to carefully explore the main pros and cons as well as the possible consequences of our actions before depending on the policy to adopt, or we need to define a new policy. Right. I guess this is in reinforcement learning. We talk about policies and all this. So when there are two or more diverging policies offered by the system, and we need to see which one to adopt. Careful reasoning based on inference and counterfactuals. Counterfactual is something we say it is not true, but what if, that kind of a thing, right? What if this happens, right? What if a particular war hadn't happened? What could be the situation between these two countries? Something like that, right? It's not a real thing. You're just imagining something like that, counterfactual. And to be a system 2 capability supported by system 1's heuristics to reduce the search space. So you have a reasoning system with counterfactuals, and then you want to work with the first one to deal with scenarios, right? Okay, so reasoning using both systems 1 and 2. Ethics theory is tied to systems 1 and 2, deciding if a certain action is morally acceptable or not. How humans switch between these different approaches in judging the morality of an action, how divergence can be defined in an ethical context, how to define methodologies for ethical reasoning in AI. All right. Actually, I have two sets of slides on ethics in AI and explainable AI, where we are going to talk about very specific solutions for explainable AI and ethical AI. So I think it will become clear. Right now, it seems a little vague, but there are references here, which is kind of interesting. Judging the morality of an action, right? Does the car decide to kill somebody, or does the car decide to jump off a cliff, right? Something like that. Which is what is the ethical action? Should the car go turn left or turn right? One would cause harm to somebody, the other one would cause harm to the passenger, right? Things like that. And there are all kinds of interesting, intriguing issues here. Okay, abstraction, attention, knowledge graphs. How to deploy skills and problem-solving capabilities were probably acquired in another environment into the new one. Recognize similarities and differences between the two environments, and to use this knowledge to decide what to temporarily forget during the abstraction step. My next lecture on robust AI will talk a little bit more about this idea of abstraction, causality, things like that. How do we define abstraction? Generalization mechanisms that are guided by a notion of attention and pass from a raw data level to a more abstract level. I think there is a concrete example here. On this problem of fizzbuzz, you're constantly, in the fizzbuzz, the way you implement it with the neural network is the input number. Let's say I say it's 153. You would represent 153 as maybe a 10-bit number. The input would not be a decimal number, but it would be in a binary string. And that input string has to be mapped into one of four values, right? Fizz buzz or the number itself. And so in this mechanism, it's performing this task of mapping that, but with no abstraction going on here at all. That the number has some factors based on 3 and 5 and so on. That concept is completely missing in the solution to the problem. And how do we get a notion of attention and pass from the raw data to a more abstract level? They say, this is what's happening. Maybe an attention model or something is used. So saying you learn that in this, the logic for this problem is divisibility by 3 and 5 and 3 and 5, that kind of thing. And once it's learned, it's now passed along to the other one, so notion. So this is passed from the raw data level to a more abstract level. What does it mean for knowledge to be explicit? Is it related to the presence of metadata, structured knowledge graphs, language related entities? Okay. Combining multi-agent systems. In a multi-agent view of several AI systems communicating and learning from each other, how to exploit, adapt current results on epistemic reasoning and planning to build learned models of the world and of others. So this is the standard multi-agent problem. When you have multi-agents, how do you cooperate? I think in reinforcement learning, they do this all the time, of having multi-agents cooperating to solve a problem. And the same thing here, you can think of the two modules as multi-agents. And so it becomes a problem of combining multi-agents to solve a problem. And architectures for supporting this vision of AI. So AI systems should include several independent simple components to be triggered when needed according to a governance model. Right. So this says, so there is some kind of a governance model. It kind of, I think we've stated it already, but several independent simple components that interact, and the individual agents focus on specific skills and problems, act asynchronously, contribute to building models of the world, of other AI systems or of self, and can be combined in many ways. So all of this. So this is simply a proposal paper which we've just discussed. There's Kahnemann's AI. It's got 10 different possible research areas, and you can think about these and expand upon each. And I think they give a little bit more detail than what I have given here. You can take a look at the source to see what exactly each problem might mean, what are the references. And so that's what's here. So it's a range of problems which are, some of which are more concrete than others, as some of the questions you asked about the division between the two, capability, sequentiality, metrics, how do you evaluate, introspection, switching, how to reason with both ethics theories, and then definition of abstraction, and how do we go from examples to a concept, and combining multi-agent systems. Concepts are the essential thing that distinguish human beings from animals, in terms of we have this idea of abstraction, and we can carry along telling stories, for example. Human beings can do that, which other other animals cannot do, and so on. Okay, so that is this part. Let's do a little bit of the next part since we have time. I don't want to lose too much time. And so what I have next is, after research topics, is something called robust AI. Robust artificial intelligence. So we've talked about a solution, and now we're going to talk about the problem. It should have been the other way around, but that's okay. I just wanted to introduce Kahnemann first as a possible solution, but now let's talk about the problem a little bit more. Okay, so this is, again, in a way, a little bit of a repeat of the opening one about shortcomings of today's deep learning. Robust artificial intelligence is, again, a reiteration of those in more detail. So if you want a paper on this, the next decade in AI, 4 steps towards robust artificial intelligence. So what some people are predicting is during the next 10 years, we're talking about 2021 to 2030, let's say, where is going to be the action in AI? Of course, we're on the top of deep learning right now and realizing some of the limitations. And the argument here is we are going to be wanting more robust artificial intelligence during the next 10 years. So what are these topics? So the topics here are that there are limitations to neural networks. And then we say symbolic methods are useful. They could be useful to deal with the challenge of neural networks or the shortcomings of neural network limitations. And then how do we combine the two together? We just talked about that using the different architectures. And then the discussion is towards an intelligence framed around enduring abstract knowledge. Is there anything else we can do? Seeing the whole elephant a little bit at a time. Conclusions, prospects, and implications. So these are some of the topics that are coming up. So what do we mean by robust AI? So robust AI is intelligence not necessarily superhuman or self-improving. Right. So this is not necessarily that it's so smart, right? But applies its knowledge to a wide range of problems reliably. So it says it can apply what it knows to a wide range of problems. Reliably is underlined here. It synthesizes knowledge from a variety of sources to be able to reason flexibly and dynamically about the world. Right? Flexibly and dynamically. And then transferring what it learns in one context to another in the way that we would expect of an ordinary adult. Right? So we can't teach every single instance. In a way, that's, you can say, that is the shortcoming of deep learning. You train on more and more and more data, large amounts of data, and it learns all of that extremely well and also generalizes beyond the data set. But still, can it go into a totally different context in the way we would expect of an ordinary adult? Contrast with narrow intelligence, pointillistic intelligence. So robust AI is to reliably perform, but show me some counterexamples. Narrow intelligence. Narrow intelligence is not robust intelligence. Systems that perform a single narrow goal extremely well. Example, chess playing or identifying dog breeds, right? You have trained a neural network, which is a supervised learning problem where we train it on, like Alsatians and, the golden retrievers and all kinds of dog breeds. And it does a pretty good job when it sees a new image and saying what kind of dog it is. So narrow intelligence it does very well on these, often in ways that are extremely centered around a single task. Right, single task it can do very well. But we say that is not robust and transferable to even modest differences. So let's say a chess playing program to a board of a different size, or from one video game to another with the same logic, but different characters and settings without extensive retraining. So narrow intelligence it can does very well on this size of board, and you specify these, it does extremely well, or these dogs, but can you transfer it to cats, right? I mean, we say that is transfer learning. You'll have to kind of again use what has been learned in from one domain and use a different set of data to retrain it and so on. So you get a good starting point, but can it simply transfer over to the other? Narrow intelligence cannot do that. And pointillistic intelligence is intelligence that works in many cases, but fails in many other cases, ostensibly quite similar unpredictably. So there are peculiar circumstances you see, you use it and say, oh, wow, we never encounter that. So a visual system that recognizes school buses in general. Let's say we are an autonomous vehicle that has recognized school buses, but fails to recognize a school bus tipped over its side in the context of a snowy road. I guess it's a good Buffalo example here. There's a snowy road and this bus has fallen down, and it's not able to recognize that this is a school bus. And it's kind of unpredictable, right? I mean, this is kind of a rare circumstance. And here is another one, a reading system that interprets some sentences correctly, but fails in the presence of unrelated distractor material. So a paragraph about football here, and it is able to recognize all of this stuff, and they put in some sentence here. Maybe I should expand this view into, right? Maybe I should have been doing this all along. So we have a Super Bowl 50. Peyton Manning became the first quarterback ever, two different teams, two multiple Super Bowls. He's also the oldest quarterback ever to play. So this is old news before Tom Brady, right? The past record was held by John Elway and Broncos, etc. So on. And quarterback Jeff Dean had a jersey number 37 in Champ Bowl something. So the one last sentence, they threw it in. That was not question. What is the name of the quarterback who was 38 in Super Bowl 23? And original prediction was John Elway. John Elway is the correct answer. Prediction under adversary. So they threw in an extra sentence. Quarterback Gene Dean had a jersey number in Champ Bowl 24. His answer is Jeff Dean. So intelligence works in many cases, but fails in many others, ostensibly quite similar unpredictably. So both these examples show some unpredictability of the situation, because it is not close to the data set that it was trained on. Shortcoming of deep learning. And what do people at Facebook say? Facebook AI, regularization, 2019 paper. A growing body of evidence shows that state-of-the-art models learn to exploit spurious statistical patterns in data sets instead of learning meaning in the flexible and generalizable way that humans do. All right, so they observed this. The models are doing well, but they're learning spurious statistical patterns. Something that is totally irrelevant, it is finding something about color or whatever it is, that it's finding some correlations existing there. It's finding it out, but it's not useful and not the kind of things that human beings might learn. A key weakness, Benji, again, not too long ago, right? Less than 2 years ago. Current machine learning methods seem weak when they're required to generalize beyond the training distribution, which is what is often needed in practice. So again, we come back to this issue of generalization. We spend a lot of time in the deep learning course saying generalization, regularization, and so on, and so many sophisticated methods such as a dropout and so on, right? But come down to it, we're saying that's a key weakness is when you go outside of the cloud of the data, far from the cloud, it hasn't learned the concept. So here is deep learning. We talk about this particular deep learning model, BERT. This slide I just have, I took it from one of my attention model slides from the deep learning course. So we have a basic encoder, decoder, RNN model here, right? Recurrent neural networks. And encoder, decoder, there's context here and so on. Encoder, decoder, RNN with attention model. All right, so there is an attention model that somehow summarizes the input data. And then we have transformer model with no recurrence here. And then the generative pre-training of attention models. And then BERT with no decoder using bidirectionality. So this is some kind of a machine translation type of model. We are going from input to output, string to string type of thing, right? That's what it is. So this is a recurrent neural network with attention, transformer with no recurrence, and then generative pre-training attention model, and BERT no decoder using bidirectional. So many such models exist. And the point we're going to make is with all of this, the shortcomings. GPT-2 generates human-like output, trained to predict next word. Like if you type into GPT-2, the cat sat on the, it's going to give all these options as the next word. The cat sat on the floor, bed, couch, ground, table, etc. Probability of floor is the highest probability. And while trained to predict the next word, it surprisingly learned basic competence in tasks like machine translation and question answering. That's without ever being told that it'd be evaluated on those tasks. So GPT-2, very impressive. Not only was it able to predict these words, it was trained to predict the next word, but surprisingly learned basic competence in machine translation and so on. Okay, this example I think I gave already. Let me read it again. GPT-2 generalized synthetic text. System prompt, human written. In a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researchers was the fact that the unicorns spoke perfect English. And the model completion, I mean, it's kind of a nonsensical thing that you would find unicorn itself doesn't exist, and speaking perfect English is even more ridiculous. The scientists named the population after the distinctive horn of its unicorn. These four-horned silver white unicorns were previously unknown to science. After almost 2 centuries, the mystery of what sparked this odd phenomenon is finally solved. It's made up all this stuff. Dr. Jorge Perez, a evolutionary biologist from University of La Paz, and several other companions were exploring the Andes Mountains. Perez and others ventured further into the valley. By the time we reached the top of one peak, the water looked blue with some crystals on top, said Perez. Perez and his friends were astonished to see the unicorn herd. These creatures could be seen from the air without having to, so on. The whole story being made out of a nonsensical sentence. Right? And all right, so that's the kind of thing GPT-2 can do. It's very impressive. But does it show deep understanding? Ability not only to correlate and discern subtle patterns in complex data sets, but also capacity to look at any scenario and address questions such as a journalist may ask: who, what, where, why, when, and how. GPT-2 ostensibly reflects deep understanding. Plausible continuation. Two soldiers walked into a bar, right? The completion it gave is in Mosul and spent all their money on drinks. That sounds pretty reasonable. Sounds like you know what two soldiers walking into a bar may do. This is saying they spent all their money on drinks. But failed continuation. Yesterday, I dropped my clothes off at the dry cleaners and have yet to, the other way around, and have yet to pick them up. Where are my clothes? It is saying at my mom's house, right? So it says you just said you dropped your clothes off at the dry cleaners, is not able to even keep track of that. It's a failed continuation. And such errors are widespread. We will clearly need a more stable substrate in order to achieve robustness. So at a surface level, they look great. Sometimes, right? Two soldiers walked into a bar and they spent their money on drinks. That's a reasonable answer. Whereas this one is can't even able to understand what was said. So what is needed for robust AI? Return to the three concerns of classical AI. Knowledge, internal models, reasoning, but with the hope of addressing them in new ways with a modern palette of techniques. And each of these concerns was central in classical AI. So I'm saying that a robust AI that is doesn't fail should somehow incorporate knowledge, should incorporate internal models, should have reasoning. Of course, something like this, we have all of this in deep learning, but the classical AI, I was talking about it, and that's what it can offer. And what GPT-2 lacks is no explicit common sense knowledge, no explicit reasoning, and no explicit cognitive models of the world that it tries to discuss. Right, so these are the things that GPT-2 is a pure deep learning solution to the problem of NLP. Contrast with a deep data-driven approach, GPT-2 characterizes trend away from classical AI. So it's moving away towards a data-driven paradigm of deep learning. That's what deep learning is all about. It data-driven and moving away from the classical AI. And deep learning has had successes. The Atari game system plays a wide variety of games without any use of detailed cognitive models. So that deep learning solutions, I think that was a reinforcement learning solution. Atari game system plays a wide variety of games without any detailed cognitive models. Sutton, who wrote a book on reinforcement learning, says on deep learning, the only thing that matters in the long run is the leveraging of computation. Human knowledge approach tends to complicate methods in ways that make them less suited to taking advantage of general methods leveraging computation. So the deep learning folks who worked with reinforcement learning saying the knowledge-based approach tends to complicate the model. So they were not very supportive. All right, limitation of large corpora. Even with massive amounts of data and new architectures, transformers, which underline GPT-2, knowledge gathered by neural networks remains spotty and pointillistic, useful but never reliable. So these models are useful, like in Alexa, but not reliable. Common sense not induced from large corpora. Those of you who are working with Alexa or NLP and know of these shortcomings, maybe you can begin there and you can say, what are the shortcomings you have observed that it cannot do? Bring to the table saying, look, it cannot do these kinds of things. So how should that be addressed? So anyway, those are all starting points to find problems to solve. Model building is hard and it would be easier if that too could be skipped. Some more GPT-2 blunders. If you break a glass bottle of water, the water will probably fill the sentence. This is a rule. If you break a glass bottle of water, the water will probably, another longer one, break some more and splatter on the floor. Water creates bubbles which expand when the amount of water in the bottle increases. Right? The correct answer would be the water. If you break a bottle of glass, the water will probably spill. I guess that should have been the answer. If you break a glass bottle that only holds toy soldiers, the toy soldiers will probably follow you in there, something nonsensical. So there are all these kinds of blunders of the most sophisticated natural language processing systems are missing because it's missing some kind of a model of the world and so on, common sense knowledge and so on. So these are all identifying why do we need something more? Why can't we just stop saying we know all about deep learning? Is that's enough? The cognitive science perspective, cognition cycle. The cognitive science people have been doing these kinds of things for a long time. Organisms, example, humans, take in perceptual information from the outside. They build internal cognitive models based on their perception of their information. Then they make decisions with respect to those cognitive models, which might include information about what sort of entities there are in the external world, what their properties are, and how those entities. This says, how do human psychology people who build cognitive models and what do? They talk about organisms, models, and reasoning and decisions with those. So they're saying organisms, that is, they're trying to explain how do human beings do this. We take perception from the outside, we build cognitive models based on their perception of that information, and then they make decisions with respect to the cognitive models. And the view of cognitive scientists is that cognitive models may be incomplete or inaccurate, but seen as central to how an organism views the world. So they build these models, more and more sophisticated models. That's what they try and do. Examples of cognitive model-based approaches. Okay, lots of examples of this. Video games. This is a non-deep learning solution, video games. An internal model of the world, model periodically updated based on the user input and activities of other entities in the game. The model tracks characters' location, health, and possessions. What happens in the game, whether or not there is a collision after a user moves in a particular direction, so on. So video games have an internal model of the world and the model tracks the character's location. So video games have some kind of a cognitive model built into them. If you're an NLP person, linguistics typically understand language according to a similar cycle. Words in a sentence are passed into a syntax that maps into semantics that specifies things like events, various entities participating in. And that semantics is used to dynamically update a model of the world. So in an NLP model, simply again has some kind of a model. Words in the sentence are passed into syntax, so individual sentences into semantics that specifies things that the entities participate in. So that's the semantics of words and current state and location of various entities. So that's how the model would be. Robotics, much work operates in a similar way. Perceive, update models, make decisions. Some work, particularly end-to-end deep learning for object grasping, does not do this cognitive approach. So the cognitive models are common in video games, in linguistics, even in robotics, where there is some kind of a model of the world that is, where things are laid out and so on. Like a video game has that, a robotics has that, and any kind of outside input is used to update that model, and then you make decisions based on how to move, for example, for a robot. perspective of robust AI. So we're talking about robust AI. If we do not do something analogous to this, we will not succeed in the quest for robust intelligence. Saying if we don't do something analogous to this, having a model of the world, the AI systems do not represent and reason over detailed structured models of the external world, draw on knowledge about the world and its dynamics, they will forever resemble GPT-2. So a GPT-2 will get some things right, drawing on vast correlative databases, but won't understand what's going on, and we won't be able to count on them, particularly when real world circumstances deviate from training data as they often do. Wow. So this is saying that you need to have a model of the world and change the model of the world based on real world input. And that model of the world is, we're saying, it's probably symbolic model of the world. We can always say that push the neural network to find a manifold and so on. We always argue like that, but that may not really correspond to a symbolic representation of the world. So this is saying in a symbolic representation of the world, you specifically are saying what are the entities, where are they located, so on. So if you don't do this, you will get, this is the indictment of deep learning. They'll get some things right. Deep learning will get some things right, drawing on vast correlative databases. So you have large databases, but they don't understand what's going on. Here is a simple example of deep learning and the identity function. So this is a simple deep learning network. Input is 8421, hidden layer is H1, H2, output is 8421. This is supposed to learn the identity function. Input is 0010, output is 0010. Input is 1000, output is 1000. Input is 1010, output is 1010. Input is 0100, output is 0100. So this is, and you present now a test input 1110, and typical test output is 1110. Test input is 1100 and you get 1100. Test input 0110, 0110. Typical test output. What about this? Test input. Typical human response for all of these 0011, 1001, 1101, you're getting the right answer. Typical test output. Think 0011, it's giving you one off here. The last bit is off. 1001, the last bit is off. 1101, the last bit is off. One more bit is off. 1111, one bit is off. So there is something happening here is that for certain, this is the data, input data, and it learned on that. On some of these inputs, it's getting the right output. On some of the others, while a human being has no problem, the human being also has not seen all these. But looking at this example, the human being learns that the input output are the same, so you just reproduce that. Whereas this one is looking at something the hidden units are producing here that is off, the last bit and so on is off. And it's producing these incorrect values. Within canonical neural network architectures, non-uniform extension of broad universals. So this is such an identity. We are learning that there is a certain universal concept here, that it is identity function. It's missing that point that this is an identity function. It is somehow taking it through these hidden layers and producing the values, and hasn't learned the concept that is to reproduce the identity. My next example is the same as FizzBuzz, deep learning and FizzBuzz. Print the numbers from 1 to 100, except that the number is divisible by 3, print Fizz, divisible by 5, print Buzz, divisible by 15, print FizzBuzz. Training data was integers 100 to 1024. So there were correct answers were given. For example, for 100 is divisible by 5, right? We would say it's a buzz. 101, this answer is 101, I suppose. And like that. So you would have a training data set from here and keep on exposing it to 1,000 epochs of different samples of this. The integers below 100 were held out as test data. So here is the code and so on in TensorFlow, and the input and the output 185 numbers, I suppose. And then here it is. It's printing out 1, 2 Fizz, 4 Buzz, Fizz, 7, 8 Fizz, Buzz, like that. I think 98, 99, 100. For 99, it gives Fizz. For 100, this should have been Buzz. It's getting it as Fizz here. So there are a few mistakes in this program. It was done by a machine learning program with one hidden layer, and there's a data set. It's getting it accuracy 99%. But it hasn't learned the concept about divisible by 3, divisible by 5, and it is just going by some matching of the bits, which is missing the concept. Regularization versus large training data. Artificial neural networks are powerful function approximators capable of modeling solutions to a wide variety of problems, both supervised and unsupervised. As their size and expressivity increases, so too does variance of the model, yielding nearly ubiquitous overfitting problem. So as you make it with more and more units and layers and so on, comes overfitting. Although mitigated by a variety of model regularization methods, the common cure is to seek large amounts of training data, which is not necessarily easily obtained. So we're saying in NLP, for example, the common cure has been to get much more data. In other cases, we increase its expressivity by increasing the number of layers and so on. So we then jump to saying, what is happening with neural network? Neural network limitation. Neural nets excel at two things: memorizing training examples. They can do that, but that we call it as overfitting. And interpolating within a cloud of points that surround those examples in some cluster of hyperdimensional space. So it is saying you got some examples here of these bit strings, and these green ones are all correct, I suppose. So these are the bits that are trained on, and it's giving you good examples around them. But if you get points outside, so it's going to get them wrong. Poor at generalizing the identity function. These examples were all for the identity function. And outside the space of training examples, it is saying it is making mistakes on outside of this. So what is happening with deep learning neural nets? Two related neural net problems: idiosyncrasy and excessive dependency on training regimen. Lack generalizing beyond training examples and cannot be trusted in open-ended domains. And poor when pushed beyond the training distribution. So it is saying outside of the distribution, it's able to get it for the distribution, but it falls apart. A math learning system was good at 1 plus 1 equal to 2, 1 plus 1 plus 1 equal to 3, up to 1 plus 1 plus 1 plus 1 plus 1 equal to 6, but fell apart for 1 plus 1 plus 1 plus 1 plus 1 plus equal to 7 and all larger examples. So this is what we're saying is it performance is kind of limited by the training data. Excessive dependency on training regimen, sensitive to exact details such as the order in which training items are presented, and the generalization can depend critically on the environment. All right, I think we're at the midway point here. So I think what we're going to do is we'll stop at this point today, and we will take up okay, so we'll stop at that point, and so we will continue our study of this robust AI, and we will discuss a few other papers and topics. There's a paper called Symbolic AI, the third wave. So after this robust AI is over, I'm thinking of going into that, and then we'll also discuss the probabilistic graphical model learning and so on. So meanwhile, think about some problems where you have got both a symbolic solution and a machine learning, deep learning solution, and even the example of FizzBuzz lends itself to both problems, and how one could possibly explore that, right? Okay, so I shall see you all next week. Some students, I had said I'll meet you after class, GRU, but let's postpone that. We've had a long class today, and we can have another offline discussion. Okay.
Sure,
All right, then.
Professor.
Thank you all. Any other questions?
Thank you.
Professor, I didn't say